Welcome viewers, you are welcome back to O3 School app. Remember, the app is not just for JAMB, equally have for WAEC students, all right? Mind you, the app is quite available in your Play Store and Apple Store. Do well to install the app and also activate the app so they have full license, all right? Now, on today's physics, we're going to be talking about wave motions. Wave motions. First, let's talk about motions. All right. Now, we know that motion is a change in position of a body depending on time, which takes place in any direction. Now, we are talking about wave now. All right. It means particles in motions. Particles in motions. Now, wave is actually a disturbance. Wave is a what? A disturbance. All right? Wave is a disturbance that transfers energy in form of kinetic energy from one point to another without causing any permanent displacement to its medium. So, wave is a disturbance. All right? Wave is a form of vibration or a kind of oscillations that conveys energy from one point to another. Now, this wave can move through liquid, gases, and even solid. Liquid, gases, solid, and even empty space. Empty space. So when we say empty space, we are talking about the vacuum. Vacuum. So wave is a disturbance that transfers kinetic energy or transfer energy from one medium to another, from one point to another, without causing any permanent displacement to its medium. Now we have what we call the major factors we'll be considering or what we'll be deliberating on is mostly wave equations, wave relationship parameters. All right? Wave relationship parameters and terms and changes. Another is terms associated with wave. Then another thing is wave representation. All right. So wave is a disturbance. It can move through solid, gaseous, or liquid, gaseous, solid, or even empty space. So we'll be deliberating on wave equations and even kinds of waves in this particular episode. All right. So the wave motion will be split into different kind of parts. So in this first part, this is just the introductory part. We just made just for you to be conversant with the concept of wave. The wave is a particles, all right, that conveys energy from one point to what? Another. Now, this wave has some scientific and practical applications, all right? For example, we talk about the radio waves. The radio waves. When we talk about radio waves, that is under telecommunication. For a very long distance communication, you employ the radio waves. All right. Now, telecommunication, you talk about a very long distance communication. So this wave conveys information, all right, in form of energy from one point to what? To another. So Radio wave is one practical application of what? Of the wave motions. Now, when we talk about the empty space, that will take us to another concept again, which is the classification of waves. Now, when it comes to classification of waves, we have the mechanical wave, and the electromagnetic waves. All right? Now, when you talk about the mechanical waves, these are waves that require medium for their propagations. All right? A very good example is water waves, sound wave. For water wave, if you throw a particular stone inside a pool of water or in a swimming pool, what you get is ripples of what? Of water. That is it. The medium now is water. We can also plug a guitar string. That medium is the string. Those are mechanical waves. Or even it could even be waves on a rope. All right? Wave on a rope is also a kind of what? Mechanical waves. So mechanical waves, they are waves that require medium for their what? Propagations. Now, when it comes to electromagnetic waves, that means there's presence of electric and magnetic. That's why you call it the electromagnetic waves. Now, in the case of electromagnetic waves, they do not require any material medium for their what? Propagations. So these waves, they move in empty space. All right? Empty space, and that is called the vacuum. Now, this kind of wave, they can move as far as 500 kilometers, as far as 6,000 kilometers, depending on their designs. All right? So imagine radio waves. Someone can be in Lagos, for instance. What happened? You get information from other countries by means of what? Electromagnetic waves. Someone can be in you can equally be in Abuja, for example, chatting someone in France. It's a result of electromagnetic waves. So they are mostly used for telecommunications. Now, under electromagnetic waves, we can equally have the visible light. All right? We can equally have the microwaves. Definitely, we can equally have the X-ray and the gamma ray, the ultraviolet ray, and even the infrared. All right? The infrared, they are under the electromagnetic waves. Now, the X-ray and the gamma rays, they involve what we call the photons. Photons, those are emissions of light. They can penetrate into solid materials. All right? In the field of mechanics, you talk about the X-rays and gamma rays. All right? To check maybe cancerous growth or cancer treatment, the use of X-rays and gamma rays, they are being applied. So that is one aspect of the classification, which is the electromagnetic waves. Now, in transmissions of signals from radio station, from TV broadcasting stations, they use what we call the principle of what? Electromagnetic waves. All right? Now, that is that on the classification. Now, I said the classifications of wave or classes of wave is based on the mechanical wave and the what? Electromagnetic wave. That the mechanical wave, they require material medium for their propagations. While the electromagnetic wave, they do not require material medium. They move in empty space or vacuum. Now, one thing is that the mechanical wave may be associated with some speed. All right? With some speed. Then we can have speed of sound in air. The speed of sound in air is approximately 330 to 340 meter per second. While the speed of sound in water, if you have done echo, all right, the speed of sound in water is about 1,500 meter per second. Now, if you observe, I may beat a drum within my a particular room. It can be held maybe close to the gate. But as more and more far the distance, all right, the sound will definitely be truncated. The sound will not be able to move as far as maybe 50 meters or even 100 meters, all right? So you see that there is a distinction between mechanical wave and electromagnetic wave. Electromagnetic wave can move as far as 2 or more countries. In fact, it can even connect the entire universe. That is the essence of the electromagnetic waves, all right? Now, compared to the mechanical wave. The mechanical wave is just within a short period of time. Now, that means that the electromagnetic wave is associated with the speed of light. Is associated with the speed of light. All right, that's about 3 times 10 raised per 8 meter per second. That's about 300 millimeter per second. That's the speed of light. So you can't use the speed of light to compare the speed of sound in air, which is 340. Speed of sound in water, which is 1500. No. So you see, this magnitude of the speed of light is about 300 millimeter per second. So that is that on the classifications of wave. So let's see. Another thing we need to understand again is the kinds of waves. All right? What are the kinds of waves? We have the transverse waves, all right, and the longitudinal waves. Now, what happened is that under the transverse wave and the longitudinal waves, here we talk about a kind of relationship between the direction of the particle, all right, and direction of energy transferred, all right, direction of energy transferred. Now, for transverse wave, right, the direction of energy transfer is perpendicular to the direction of the particle. So if it's perpendicular, it means at 90 degrees, all right, is at 90 degrees. But when it comes to the longitudinal waves, it is parallel, all right? The direction of what? The direction of particle to direction of energy transfer for longitudinal waves is what? Is parallel. While that of transverse, it is what? Perpendicular. So that is just the difference between that. Now, another thing we need to know again is the wave. Now, let me show. Now, when it comes to transverse, let me show something of this form. Something of this form. Let's say we have, all right. If this is direction of energy, all right, it is perpendicular to the direction of what? Of particle, all right. Then the part where you have more of the wave particles is called a point of compression, all right. While the part where there is a loose in the compression, loose in the wave particles, we call it the refractions, all right. So that means we have compression and we have the refractions. Now, what happens is that the direction of particles here is perpendicular to the direction of energy transfer. So if it's perpendicular, it is said to be a transverse wave. But if it's parallel, all right, remember parallel lines, they never meet. But if they are both parallel, it is said to be what? Long. Now, the major thing is that the two kinds of wave, they both convey energy, all right? Remember that wave, as I've earlier said, wave motion is the motion of particles in the sense that they transfer disturbance, vibrations from one medium to what? To another. Now, our major concern now again is the wave relationship parameters. All right? So let's see wave relationship parameters. Now, for wave relationship parameters, all right, it involves, let me have a diagram here. So we have maybe a sinusoidal waveform, all right, goes this way, like this. Now, if you watch this point, from this point to this point, it's called amplitude, all right? This is called the amplitude. So the amplitude is one parameter employed in wave, not just in wave, even in AC circuit, in alternating current, because amplitude is the maximum displacement of wave particles from rest, all right? So the maximum displacement of wave particle from rest position is the amplitude. Now, if this is amplitude, here we have crest, all right? So let's say this is crest. This is another crest, all right? If this is trough, here's another trough, all right? Now, what happened is that here we have what we call the displacement, while here, all right, here is x, and this x is the horizontal distance, while the y here is displacement. This is displacement. Now, this is amplitude and this is crest. Now, if we have two successive crests, all right, two successive crests is going to generate what we call a wavelength, which is lambda. You must have the lambda, all right? Now, that means we have two successive crests. Basically, if we also have two successive trough, and that will also give us another wavelength. So we have another parameter, which is we have wavelength, we have frequency, period. We also have the angular velocity, or you can call it angular speed, all right? So we have amplitude, we have displacement, we have wave constant, which is K, wave constant, all right? We have the horizontal distance, all right, which is X. Now for wavelength, this is lambda, this is F, period, this is T, angular velocity, this is omega, amplitude, which is A, displacement, which is Y, wave constant, which is K, and horizontal distance, which is X. Now, what happened is that from here to here, it is half circle, and half circle is pi, all right? But two circle, it's two pi. Now, at pi, that's 180 degree. At 2 pi, that is 360 degree. So if this is just a semicircle, I have another semicircle. Now, this is the positive amplitude. Then at this point, we call it the negative peak value. Negative peak value, or the negative amplitude. So this is a negative amplitude. All right? So what happens is that there is a rise and fall. There is a rise and fall. And that is alternating quantity. For every instantaneous values of alternating quantity, there is always a rise and fall. And that's why it's called a sinusoidal waveform. Now, what is wavelength? I said wavelength is two successive crests, all right? Or the two successive trough will give us wavelength. Now, what is frequency? So let's discuss more on the frequency. Now, for frequency, F. Now, frequency is what? The numbers of oscillation or number of vibration over number of or per time, right? Not per time. So number of oscillations per time, that will give us the frequency. Now, the time taken to complete a circle, that is the period. All right. So that means there is an inverse relationship between frequency and period. So that means frequency is the inverse of period. Now, if frequency is inverse of period, what happens to our angular velocity? Now, if I have a circle, all right, angular, the speed moving in a circular path give rise to angular velocity, and that is omega. All right. So that means omega is 2 pi what? Is 2 pi f. Now, if omega is 2 pi f, and my f is the inverse of period, so definitely omega is 2 pi over t. All right. Omega is 2 pi over t. Now, there's another relationship. Now, what's that relationship? Now, the relationship is between frequency. Now, this relationship is mostly used by most of the radio stations. We have it. The velocity is equals to f lambda. All right. If velocity equals to f lambda, that means lambda is velocity over frequency. Now, this formula may be very small, but is very key. Why is it so vital? The reason is that in most radio stations and television stations, in transmissions of signals, all right, the frequency is very paramount. It's very key. And the wavelength tells us the length of the antenna is also very key. Now imagine we have antenna that is so wide, right, or that link a particular country to another country. That means the cost to convey information will be very exorbitant, so expensive. All right. Now, what happened is that they try to increase the radiating power of the frequency so as to reduce the what? So as to reduce the what? The antenna size. All right. So that is why you see most antenna size may be 150 meters, while the frequency may be 560 megahertz, or 200 megahertz. Sometimes you see 99.5 kilohertz. So there is increment in the frequency while there's a reduction in the what? In the wavelength. All right. So this formula is very key. Now, the velocity employed is the velocity of is the speed of light, which is about what? 3 times 10 raised per 8 meter per second. All right. So let's see. There is a frequency velocity relationship. So that means V is equals to F lambda. All right. If V equals to F lambda, now we need the antenna size. So lambda is velocity over what? Over frequency. Now, what is velocity? The velocity of light or the speed of light is about 3 times 10 raised per 8, right? Meter per second. Over. Now, there is a carrier frequency. Carrier frequency of 2000 megahertz. Or let's say, okay. Let's say let's use 200 megahertz. All right. Carrier frequency of 200 megahertz. The meaning of carrier frequency is that we have audio signal and carrier frequency. All right. Now, the audio the audio signal is very small. For example, as I speak now, my audience within 10 meters from where I'm standing will be able to hear me. But if I have audience that are 100 meters from where I'm standing, they won't be able to hear me because at that point, my audio signal will be weak for them to hear. Now, what happens is that there's a need for carrier frequency that tends to envelope my audio signal. All right. Now, when the audio signal is being enveloped by the carrier frequency can now move it. All right. Can now transmit it to a very far distance. That is what happened. That's the principle behind your radio broadcasting, your TV broadcasting. Whatever they are saying in that studio, whatever you are hearing from the broadcaster or the newscaster is the audio signal. All right. So what happened is that the audio signal will be enveloped into the carrier frequency. All right. Then what happened? It will be what? Encoded. When the signals are encoded, what happened? There will be a kind of what? You decode it. That's why most of your houses, you have your decoder. The decoder now filter the carrier frequency from the audio signal. Then what happened? The carrier frequency now become unwanted. What you have now is now the audio signal. You will be able to hear the person from that radio station. So that is the help of the carrier frequency. Now this is velocity over frequency. So 3 times 10 raised per 8 meter per second over the frequency. What is the frequency? 200 megahertz. So 200 megahertz. Mega is 10 raised per 6. So times 10 raised per 6. All right? Becomes hertz. Now what happens is we have 3 times 10 raised per 8 over 200 times 10 raised to power 6. That's about 2 times 10 raised to power 8. All right? 10 raised to power 8, we cancel 10 raised to power 8. We have about 3 over 2. That's about 1.5 meters. So look at the antenna now. The antenna size is so small, while the frequency is so high. All right? So now the radiating power, all right, the radiating power is to create a carrier frequency of 200 megahertz so as to convey signals to a very long distance. So that is another application of what? Your wave motions. That's the practical application. So look at the lambda value. The lambda value is about 1.5 meters. While the what? The radiating frequency is about 200 megahertz. All right. So that is that on velocity, frequency, and lambda relationship. All right. So let's move ahead. The next thing we're going to do now is the wave equations. All right. So let's see wave equation. Now, wave, they are particles, they are oscillating. Just because they are oscillating, they are also vibrating. So in that case, we're going to have a sinusoidal waveform. Sinusoidal waveform, all right? Let's say we have something in this form. Now here, remember this point is your peak value, all right? Is your peak value. So this is y in centimeters, and this is your x in what? In centimeters. So if we assume maybe from here to this point, all right, is about one seconds. All right, from here to here is about 1 second. That is our period, and that period is our t. All right. Now we know that y equals to a sine omega t. Y equals to a sine omega t. So let's assume this is our equation 1. Also, y equals to a sine into omega t plus minus kx. Plus minus what? Kx. Now, what is K? As I've earlier said, K is what? Is our wave number or wave constant. And this wave number is 2 pi over lambda. 2 pi over what? Over lambda. Now, so let's say this is equation 2. Now, what is omega? Omega is 2 pi f. Or if omega is 2 pi f, so we can plug in our values that displacement, amplitude, sine, omega t. Omega is 2 pi f t, all right? Plus minus, wave number is 2 pi f, so it's 2 pi over lambda, then we have x. So this is the general wave equation. All right? So this is the general wave equation that will be employed to solve both WAEC, NECO, and JAMB problems. Now, again, we know that F is frequency. All right? So F is frequency. T is period. T is period. Now, what is A? A is amplitude. A is amplitude. All right? Lambda here is wavelength. Is wavelength. So definitely our V is equals to F lambda. If V equals to what? Is equals to F lambda. So we are going to be employing these equations to solve problems. To solve what? Problems. All right. So let's see an instance. Let's see an instance. Let's see an instance. So let's say solution to wave equations. All right? Solutions to wave equation. So let's say okay, so let's start. Now the first says calculate the amplitude. Now for you to solve this kind of problem, you must be conversant with the general wave equation, which I cycled before I wiped the board just now. You have to be conversant with that. And which states that it says y is a sine 2 pi ft plus minus 2 pi x over lambda. All right? You have to be conversant with this. Because what you do generally is comparison. You compare the given equation to the general equation. It's not something much difficult. You compare the given equation. All right? Compare the given equation with your general equation. So let's amass. Now we have the first one. We have 0.5 sine is equals to a sine. All right? So by the time sine cancels sine, our a becomes 0.5 meters. All right? If the displacement is in centimeters or meters, let's say it's a meter. All right? That is that. Amplitude, you don't have any stress. Just compare the given equation with the general equation. So the amplitude is 0.5 meters. You don't even need calculator. Amplitude is just 0.5 meters. Now, 2 says frequency. How do we get frequency? We compare again. Frequency is already here from our general equation, which states that 2 pi ft is equals to 200 pi t. 2 pi ft equals to 200 pi t. So pi can cancel pi, t can cancel t. What is left? 2f is equals to 200. All right? So over 2. 2 will cancel 2. So what is left? Frequency is 100 Hz. All right? Frequency is just 100 Hz. Now, the next thing now is to get period. All right? Next thing is to get, we've done this. All right? So the next thing is to get period. 3, period. All right? Period is 1 over frequency. Period is the reciprocal of frequency, or the inverse. So that will give me 1 over, the frequency is 100. All right? If I divide, I have 0.01 seconds. So the period is 0.01 seconds. 4 talks about, okay, period, let's say wavelength now. Now for wavelength, all right, for wavelength, we have about, now we have 0.4 pi x. In the other end of the equation, 0.4 pi x is equals to 2 pi x over what? Over lambda. So pi we cancel pi, x we cancel x. So 0.4 is equals to 2 over what? Over lambda. All right. So in that case, what we have, lambda is 2 over 4 times 10. So lambda, that is 5 meters. So the lambda is giving us 5 meters. All right. Now the next thing is wave number. 5. Wave number is k. K is 2 pi over lambda. All right. 2 pi over lambda. Now 2 pi is 22 over 7, or 3.142 times 2. That's about 6.28 or 6.29. So let's say 6.29 over lambda. Lambda is 5, so we have 5. That's about 1 point. So let's see. 6.29 divided by 5. That's about 1.26 meters. So the wave number, okay, it has no unit. So it's about 1.26. Now the next thing is 6. The speed. Speed is equals to velocity. And velocity is f lambda. Now if velocity is f lambda, all right, we have f. F is what? 100. Lambda was giving us 5. So that's about 500 meter per second. That's about 500 meter per. So this is how to amass or compute this kind of problems. All right. So remember we said wave, right? They are a form of particles. They are particles in motions. And these particles, they transfer or convey, all right, energy from one point to another. Because the kind of energy is a form of what? Disturbance. They are disturbance. They transfer energy from one point to what? To another, without causing any permanent displacement to its medium. All right. So we said that now what happened is that if you have a stone thrown into a pool of water, there will be ripples. And once there is ripples, ripples are always associated with transfers of what? Of energy. All right. Why sound wave also transfer kinetic energy. Immediately I hit a train made up of steel on the ground. The metal is so sonorous. So because metals are sonorous, they give off sound. So immediately the sound is being held from far distance. All right. So sound energy is they are associated with what? With kinetic energy. So that's why sound wave travels in air. You have sound in air. Sound wave also travels in water. So also remember I talk about the transverse wave. All right. Transverse waves, they are oscillations that are always perpendicular to the direction of what? Energy transfer. All right. But if the oscillations are parallel to the direction of energy transfer, they are not transverse wave. They becomes longitudinal waves. All right, longitudinal wave, they are always sideways. Sideways means they are parallel. Sideways means they are parallel. What is parallel? The direction of particle is sideways to the direction of energy transferred. All right, so we have already discussed on that. Okay, we still have, let's solve this problem. This can go. I think this is from a progressive wave. It said if y equals to 5 sine 2000 pi t minus 0.4 x, that we should find the wave length. For us to get the wavelength, you do comparison. You compare this equation with your general equation. What is that, your general equation? Y is a sine 2 pi ft, all right, 2 pi ft plus or minus 2 pi x over what? Over lambda. A here is amplitude, 2 pi ft plus minus 2 pi x over what? Over lambda. All right? So A is amplitude, F is frequency. So what do? You compile this. So we have minus 0.4x. Now we have plus or minus. So consider what is coming. What is coming is negative. All right? So that's why we have plus or minus. Now, minus 0.4x equals to minus 2 pi x over what? Over lambda. So what happens? Minus we cancel minus, x we cancel x. So we have 0.4 equals to 2 pi over lambda. So that means it is over 1. Lambda is 6.28 over 0.4. All right? So that should give us, let's see. Let me use my calc and see. So we have 6.28 divided by 0.4. Okay, so the answer is 15.7. 15.7 meters. So the correct answer is B. The correct answer there is B. All right? So that is that on that questions. So before we solve problem from our app, let's still do some kind of recap. All right? We said the major classes of wave. You say in O3 school, we try as much as possible to inculcate more of this physics, all right, to our students before solving problems. That is one thing we do over here. We try to teach first, so that we even try to make a kind of recap going back to the previous minute of the video, so as to make sure that you understand. And if you find anything difficult, don't hesitate to send us message. All right. Now we said the major classes of wave, they are the mechanical waves and the electromagnetic waves. Now for the mechanical waves, they require material medium for their propagations. Water waves, sound waves, wave on a guitar strings, wave on your rope, your drum, whatever. Those are mechanical waves because there is a medium. Now, for electromagnetic wave, they move on free space or vacuum. All right? They move on free space or vacuum. Now, we said the major kinds of wave are based on directions of their travels is the transverse wave and the longitudinal waves. All right? So the transverse waves, these are waves that travel in the direction that is perpendicular. Perpendicular means at right angle. Perpendicular means at right angle. It's at 90 degrees, all right, to the direction of disturbance, causing the wave, all right. A good example of transverse wave is your light waves, radio waves, and even the water waves. Now, for longitudinal waves, these ones, they are not at right angle, rather they are at sideways. They are at what? Sideways. All right, a good example is your sound waves. So let's see some problems. This one can go. This one can go. So let's see. Okay, so let's see. From our O3 School app, let's see some few questions. All right. So this is okay. JAMB 2000 question 23. A traveling wave moving from left to right has an amplitude. So when you hear the word amplitude, which is A, 0.15 meters. A frequency of, so there's F, a frequency of 550 Hz. All right? And a wavelength, lambda, is 0.01 meters. Now I said the equation describing the wave is dash. The equation describing the wave is dash. So we know that y equals to a sine, all right, a sine 2 pi x over lambda minus vt. Now, what someone may ask, where is this v coming from? Velocity is what? F lambda. All right. If velocity is f lambda, we know that omega is 2 pi f. All right. Now, what is f? F here will be omega over what? Over 2 pi. So we can equally say that y equals to a sine t pi x over lambda minus v. V is f lambda. And what is f? F is omega. So we can say omega over 2 pi. What will be left? Lambda. All right? Lambda will be left. So this is another relationship. So definitely we can say that we can equally say that y equals to a sine y equals to a sine 2 pi over lambda into x minus v minus vt. So the reason is that the velocity there is f lambda. So already we have f and lambda. So that means velocity is f lambda. Velocity is f. What is f? 550 times 0.01. All right? 550 times 1 over 100. That's about 5.5 meter per seconds. All right? 5.5 meter per seconds. So if velocity is 5.5 meter per seconds, and this is amplitude, all right, definitely we can say that y equals to 0.15 sine 200 pi into x minus 5.5 t. So the correct answer there is A. It's only A that can walk over there. All right. So we have 0.15 sine 200 pi x minus 5.5. All right. So the correct answer is A. So just know that velocity is what? Is f lambda. So let's move ahead. Right. So all right, we have another one from 2023. From 2023. Question 3. It said the equation of a wave traveling in a horizontal direction is expressed as y equals to 24 sine 3 pi over 4, 140t minus x. What is the wavelength? What is the wavelength? For exam condition, if you don't want any form of confusion, we can say 240 sine. Use your 3 pi over 4 to multiply the bracket. That will give us 3 pi times 140t over 4 minus 3 pi x over 4. So we are mostly concerned on the wavelength. All right, so we'll do a comparison. What is that comparison? Y is a sine 2 pi ft plus minus 2 pi x over lambda. All right, so we are more concerned with the wavelength because the question says, what is the wavelength? So we have minus 3 pi x over 4 equals to minus 2 pi x over what? Over lambda. So pi can cancel pi, x can cancel x, minus can cancel minus. So we are left with 3 over 4 equals to 2 over what? Over lambda. All right. So we can say that lambda is 4 times 2 over 3. And that's 8 over 3. All right. We have 8 over 3. All right. So definitely in decimal, 8 over 3 is about 2.67 meters. So this is how to solve that kind of problem. What you do, remove this 3 pi over 4, use it to open the bracket by multiplying to the bracket. So this is your general wave equation. General wave equation. All right. Now, because of this, your general wave equation, you compare it with what is given. What is given is minus 3 pi x over 4. Then you have 2 pi x over lambda. You compare. So you have what? 8. So this is 8 over 3. That's about 2.67 meters. That is that for that question. So we have another one, 1992. Now, 1992, question 20. All right. This one says the equation of a wave is given. The equation of a wave is given as y equals to 0.005 sine 0.5x minus 200t. It says where x and y are in meters and t is in seconds. What is the velocity of the wave? Wow. In this kind of problem, for you to get velocity, you must get f and lambda. So this is wave relationship. You must get f and lambda. All right. The reason is velocity is what? Is f lambda. So if velocity is f lambda, all right. So we need lambda. We need frequency. So let's start with the frequency. What do? We do our comparison. Again, everything abide to the general wave equation. So a sine 2 pi ft plus minus 2 pi x over lambda. All right. So in this case, here is minus 200 pi t. So we have minus 2 pi ft equals to minus 200 t. All right. So t can cancel t. So we have minus can go. So we have 2 pi f equals to 200. 2 pi is 6.28 f 200. How did I get 6.28? Now for us to get 6.28, this is 2 pi. Pi is 22 over 7. So 22 over 7 times 2. That will give us approximately 6.28. All right. So the frequency is 200 over 6.28. So if we have 200 over 6.28, 200 divided by 6.28, that's about 31.9 hence. 31.9 hence. That is that frequency. Now, the next thing is to get wavelength. How do we get wavelength? T pi x over lambda is equals to 0.5 x. S we cancel x, all right? This is 2 pi again, which is 6.28 over lambda equals to 0.5. So lambda is 6.28 over 0.5. So what is lambda? So if we do that, 6.28 divided by 0.5, that's about 12.56 meters. So this is our lambda. Now we have frequency, we have lambda. All right? We cannot come here and say velocity is frequency times lambda. What is frequency? 30, let's say approximately 32. So 31.9. This one is approximately 12.56. All right? So times 31.9. So that's approximately 400.664 meter per second. So this is our velocity. So if you check, option A says 4,000 meter per second. So the correct answer there is B. B is 400 meter, because it's approximately, if I have 401, 401 is approximately 400 meter per second. All right, 401 is approximately 400 meter per second. So that is that on that problem. Okay, so let's see again. We have this from 2021. 2021, let's see what happened. All these problems, they are all based on wave equations. So do well to absorb the general equation to your memory before entering any of the exams. All right, so let's see. In 2021, question 19, it says a wave is represented by the equation y 0.2 sine, there's a bracket there, so 0.4 pi, another bracket, x minus 60 t, bracket closed, then a full bracket. When you see question like this, you don't have to, what you do is, this 0.4 pi, use it to multiply the bracket so that you have a standard wave equations. So in doing that, 0.2 sine, you have 0.4 pi x. 0.4 times 60, I think that should be 24. 4 over 10. So that's 24. So 24 pi t. All right? So this is what you now have. This is what you have now. So if we have something in this form, all right, so what happened is, the question says, what is the velocity of the wave? So that means we need to get frequency again, all right? Because velocity is f lambda. So f is unknown. For us to get f, we bring out the general equation from the general equation. From the general equation, y equals to a sine t pi ft plus minus 2 pi x over lambda. All right? 2 pi ft plus minus 2 pi x over lambda. So you see, every of the problem we are solving, it involves the general wave equations. So let's get our frequency now. For us to get frequency, 2 pi ft, you relate to where you have t, so it's here. So minus 24 pi t. So pi we cancel pi, t we cancel t, minus also cancel minus. All right, so we are now left with 2f equals to 24 over 2 over 2. So the frequency is 12 12 Hz. So now that frequency is 12 Hz, we need wavelength. All right, wavelength is lambda. So 2 pi x over lambda equals to 0.4 pi x. So pi we cancel pi, x we cancel x. So what is left? We have 2 over lambda equals to 0.4. All right? So 0.4 is automatically, we can say 4 over 10. All right? So lambda, let's cut here. So lambda is 20 over 4. That's 5 meters. Now that lambda is 5 meters, we can then get our velocity. What is velocity? Velocity is f lambda. So velocity is f lambda. Now frequency, what is frequency? Frequency is 12 times 5. So that should be 60 meter per seconds. So that's about, okay. The answer there is B, 60 meter per seconds. All right. So if they are working in centimeters, you work with centimeters. If they are working in meters, so I think here they are working in centimeters. So we have centimeter per what? Per seconds. So that means this 5 we got is in centimeters. So the answer is 60. So that is that. On that. Now the next question is I think 2019. JAMB 2019. Question 10. Question 6 says radio waves belongs to the class of wave whose velocity is about dash. A 340, B 3 times 10 raised per 6, C 3 times 10 raised per 8, D 3 times 10 raised per 8 meter per seconds inverse. So the correct answer is C. It is 3 times 10 raised per 8. All right, because the radio waves belongs radio wave exhibits this the velocity of speed of light, and that's about 300 meters per seconds. All right. Now another thing we still need to talk about is frequency spectrum. All right. Now what the frequency spectrum is all about is it shows the range of frequencies and wavelength of electromagnetic waves. All right, they are ordered. Some have higher wavelength, like some have higher wavelength, while some have smaller frequency. All right, that's what we call the frequency spectrum. It shows the range of frequencies and wavelength of electromagnetic waves. All right. Okay. That will be all for that for this section. And in the subsequent section, we'll be treating about light energy. All right. Thank you.